Welcome to August 4th's LeetCode challenge, Path Sum 2. Given the root of a binary tree and the integer target sum, return all the root to leaf paths where each path sums equal target sum. A leaf node is a node with no children. So you're given this binary tree here with root of 5, and then it links to all this. Then you want a target sum of 22. So you want to be able to find all the paths starting from the root going down to the leaf node that sums up to 22, essentially. So that's there. So you have, for instance, 5, 4, 11, and 2, which equals to 22. Then you have 5, 8, 4, and 5. Oh yeah, the highlight in blue. Example 2 here, you want target sum of 5. However, you cannot make any you cannot make this target sum using this root node, using this binary tree, because it doesn't add up to anything. So you return an empty array. Likewise, you can't make 0 either, so you return an empty array, right, with 1 and 2. Alright, so constraints: the number of nodes in each tree is between 0 to 5,000. And the values are between 1,000 and -1,000 to 1,000. Okay, great. So a binary tree. So the approach I would automatically think of, or intuitively, is a depth first search algorithm. So we're gonna basically traverse through each of the paths, I should say, and then we're just gonna take the sum of it, and then basically we take the sum of it, and then we just basically go here, add, and then we go back, and then add, we go back, and until we get all the paths that we're looking for. So depth first search algorithm. Alright, so the first thing I'm going to do is, so the root is null, so there's nothing. So if not root, then we're going to return an empty set, an empty array, I should say. And the next thing I'm going to do is, in order to store the store the paths we're going to, or the data that we need, I'm going to use a stack or a queue. Use a queue too, but I'm going to store a stack. It's been a while since I used a stack. And then I'm going to store the output, which is going to be output. Alright, so the stack is going to be storing the root value, and the path that we're doing. So root.val. So it stores the root, the entire tree, the root. It stores the root value that we're at, and it stores the root path. Alright, that's what we want to store in our stack, our data structure. And then we're gonna have an output, which is gonna be an empty array. Alright, so we're going to do a while loop here. So while stack is not empty, exist I should say, what we're going to do is define a couple of variables that we're going to pop up from our stack. So this is the root, call it a node, I guess, node, and I'm going to call this value, and then we're going to call this the path. See, we want to make this, and we want to pop that off from the stack. Stack.pop. And I'm going to run a couple conditional statements here. So the first one is going to be if not node dot right, so the right node, and not node dot left, and the value is equal to the target sum. So basically this means that not node.right and not node.left, meaning that they're leaf nodes. So this leaf node, there's nothing to the right of it, below it, the node itself, and nothing to the left of it, the node itself. So therefore, this two statements means that it's a leaf node, so there's nothing preceding it or downstream of it. There's no descendants of any nodes afterwards. And the value is equal to the target sum. That means that it's our answer. So basically, you want to have the output dot append our path, right? Because that's what we're looking for. And then basically next thing we're going to do is basically just take the left path and the right path until we reach the end. We're going to add that to our stack. So if node.right, then what we do is stack.append. What are we going to append? Append the following. So we want to append our root, our node, I should say, node.right. And then we're also going to append the value plus the node right dot value, and then we're also gonna append our path. Let's see, path is already path is already an array, so we're gonna add that actually to our node dot right dot val. So yeah, we're gonna basically, if the right node exists, we're gonna append to the stack the right node, which is added to there. We are gonna store the value plus the right node value, which is our summation, and then we're gonna store the path of what we took to get there. Now likewise on the left side, so node dot left exists. What we're going to do is basically append to the stack the following. We're going to do node.left value plus node.left dot val. And then we're going to store the path as well. Node.left dot val. These are kind of long, and but if you just break them up, it should be somewhat readable. Hopefully I didn't make a mistake. Left, 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 yep. And then at the end of this, we want to return our output. Let's see if this runs. Finished. Okay, accepted. Awesome. So this is using a depth first search solution. Time complexity would be big O of n, because we have to iterate while using a while loop through the stack. So each stack could actually hold all the possible nodes, if worst case, I should say. Well, not in worst case, but yeah, if it has to store all the node in the stack, then we would have to run it basically big O of n times, where n is number of nodes in the tree. Space complexity is storing everything inside a stack, and the output is an array, so it holds so it'd be the size of the stack plus the output. The output is just an array, but the stack actually holds a lot more weight to it, because it has a list inside the array as well. I mean, not a list, a tuple. So yeah, it'd be a big O of 2n. So it'd be big O of n as well, because it stores everything inside the stack. Where the stack is each information here is a one root, a one node. All right. Let me let's see, am I doing recursively? Nope. Alright, that's it. Have yourself a great day, guys.